we see, in particular for micro-optics in the automotive industry. So I will briefly touch in my talk on the potential, but also a bit on the challenges. Better now? No, thank you. A bit on the challenges that we see in bringing micro-optics into the automotive applications. And finally, I will talk, of course, what we as Joanneum Research Materials are offering in terms of services to bring micro-optics into being. But first, let's start with the potential of micro-optics in automotive. Of course, the first thing that I think most of us comes to mind are micro-optics that can be used in adaptive headlights or advanced signal lights for improved visibility. With that, we're also able to improve the safety of the vehicles. However, micro-optics, of course, can also be used in sensor systems, where advanced sensor systems can be equipped with micro-optics, for example, to enhance the field of view, or potentially also for miniaturization, and by that help in advanced driver assistance systems, but also enhancing the autonomous driving capabilities in the vehicles. And last but not least, a very broader topic is also enhancements in the interior lighting of cars, so be it ambient lighting, but also to use that functional improvements in specific lighting topics, for example, also to improve or to achieve a specific illumination pattern that you want to have in the interior of the car. But when we're talking about potentials, we also need to talk about the challenges that we're facing, in particular, to bring micro-optics into the automotive industry. And the topmost challenge, of course, is related to the complex manufacturing that we have. So to generate these tiny structures in the ranges of just several tens of microns, that demands a high precision and quality control throughout the whole production process. In addition, as typical optics, these micro-optics need to be integrated in the already existing infrastructure of a car, so of the automotive application. In addition to that, there are also strong demands to the environmental durability. So the environmental conditions that the materials used for micro-optics need to withstand, of course, a broad temperature range. You have UV exposure. You also have a chemical resistance. So it's a rather harsh environment, and also that needs to be considered already during the development of these micro-optic structures. And in the end, that is a demand or a challenge that strongly will then come from the market is, once this is successful, we also need to be able, with our production processes, to maintain a high quality in a large-scale production for these components. And with that, I also already want to dive a bit into how we at Joanneum Research Materials are dealing with this. We're not just focusing on so we're focusing in general on micro-optics, but specifically we're focusing on freeform micro-optics. And why are we doing that? Well, basically, freeform micro-optics allow us a nearly unlimited freedom to shape the surface. And this, in turn, gives us the opportunity to tailor also the surface in a way that we can tailor the light distribution exactly to the requirements that our customers or that the application has. In addition, potentially, we are able to combine multiple optical elements into one single micro-optic, so different optical functionalities into one micro-optical element. And that, again, as it is general for micro-optics, of course, gives us a broad range of applications. So automotive lighting, headlights, taillights, and interior lighting we've already been talking about, but also for AR/VR applications, right? Like for head-up displays. And also for projection systems, for example, these optics can be used. And the question, of course, is how are we at Joanneum specifically working on that? So we've already established a value chain that is more or less spanning from the idea until the generated microstructures on foil in-house. And this overall process comprises of the, let's say, 4 pillars where we have the design, where we generate the simulation model. Then we have the optical simulation, where the particular ray tracing is our workhorse, where we're generating the CAD geometry. This then is transferred to the origination, and out of the origination, the first physical part of the structure is generated, and that then is replicated in our roll-to-roll nano-imprint pilot line that we have in-house. To be a bit more specific, so our optical design and simulation, which goes very strongly hand in hand, is using an advanced CAD software with a MATLAB implementation where we are using our proprietary algorithms to generate a first design. And this design, of course, is custom tailored for a specific function of these optical elements that we're using. And out of this design, there comes a precise geometric specification of the micro-optics, of the freeform micro-optics that we're using. After this first, let's say, set of design, we're forwarding this design to the ray tracing simulation, to the ray tracing software where we're doing the simulations. And with that, we have the possibility to potentially detect already very early any performance issues that we have with this part. But we're also doing kind of a pre-production verification of the component's functionality. And all of the insights we get from the ray tracing, of course, are fed back into the design. For example, if we see that there is an issue. And so, in an iterative approach, we are designing, in the end, a component where we are very confident that it is complying to the requirements that we have for the application. And these feedback loops that I've also mentioned down here, that are not only restricted to the results from ray tracing. We're also feeding, for example, our manufacturing limitations from origination as well as from replication and scale-up and replication. So that in the end, when we say, okay, our design is done, we are very confident that the design in the end, or the part that will be produced from this design, will in the end comply to what the requirements of the applications are. Yeah, so as I said, we have a design that is finished, and that of course needs to be translated from its digital form as a design to a first physical form. That is done in-house with grayscale laser lithography. So we're first creating a kind of virtual photomask, and this then is transferred on a resin master, where we have a resin stamp, and this stamp then is metallized in order to end up with a durable stamp that is ready for upscaling. Upscaling then is done by a step and repeat process. So we have successive nano imprints that are performed to replicate the microstructures on a larger area, just to give you a feeling on what size we're talking about here. So basically our master stamps are in the range of below 1 square centimeter to up to 5 times 5 square centimeters. However, our step and repeat production, or step and repeat process, is able to scale it up to a size of roughly 30 times 60 square centimeters. And this replication of this upscaling is first done on polymer machines, and these polymer machines again are metallized in order to be able to be used for roll-to-roll production. So we are creating metallized chins, which are then used in our roll-to-roll nano-imprint lithography pilot line that provides us with a continuous production process that has already demonstrated a high-resolution replication of micro and nanostructures via imprinting. And that, as a whole, gives us a cost-effective scaling of freeform optics and high volume production with a consistent quality, because we are also checking the quality of our imprints in line. But since I've not talked a lot about how we're doing it, I want to briefly present two of the case studies we've performed. The first one not in Fabulous, which was the optimization of a low beam headlight. So the basic objective was more or less to replace the complete optics that was used in an automotive headlight, a low beam headlight, with a single micro-optical, freeform micro-optical structure. So basically, with just the light source and one micro-optical element. Yeah, I think a lot of you will know the challenges that this brings with it. So we have strand asymmetries in the spread of the light, so with a very wide horizontal spread, but a very narrow vertical spread. We need a sharp cutoff line for a low beam headlight, and we have a very high concentration of light in the central area of the light distribution. And yeah, the first results we actually achieved were a bit, I would say disappointing, but disappointing is even too low to call it actually. So what you can see here is a comparison of a standard low beam system on the left side. No, it's not working. So this is the light distribution that you expect in the left column from a standard low beam system. When we were exchanging this low beam system just with the point source and the freeform micro-optics, you can already see that we didn't achieve the intensity anymore. The spread also was not there. And we had a lot of stray light. And that got even worse when we were using a 1 square millimeter LED as the light source just with a freeform micro-optical element. And the cause was something a lot of optics designers fear, the so-called étendue, that basically, very simply tells you that if you have a light source, an extended light source with a specific divergence, you're not able to squeeze all the light that comes out into a just slightly larger area and expect a very direct light out of it. So this was definitely a bottleneck where we were hitting more or less the border of physics. And upon that we said, okay, what else can we do? So we knew that a complete transformation just using freeform micro-optics could not be achieved. However, what could be achieved was at least a partial adaptation. So we could see and calculate that we could replace the projection lens that is used with a light engine with a freeform micro-optical element and end up with the same light distribution for a headlight. And this already is some progress to say, okay, we don't need a bulky lens anymore, but we can use a flat micro-optical lens. A second application that I want to show you today was an application on actual retroreflectors. So we all know these retroreflectors that are used in taillights, and I think in the US even in the headlights and on the sides. And also we know it from the bicycles where these retroreflectors are put into the wheels for better visibility. And the objective of this project was to first generate a microstructured retroreflector, of course, but in particular to enhance the aesthetics of this component, because we all know this cubic-like structure when we're looking at a retroreflector. And so our idea was to build this retroreflector up by this pyramids. And yeah, these pyramids actually are forming three surfaces. So with three surfaces, they're forming a 90-degree angle. In particular, for the replication or for origination, we were using a pixel resolution for our grayscale laser lithography of 500 nanometers. And it was also the requirement that we said, okay, we want to have a structure height below 50 microns. And with that, we ended up with 1 square centimeter of structure that is filled with more than 48,000 pyramids. You can see it also on the top right, where there's the design and also the writing data for the grayscale laser lithography. Yeah, what came out of it? On the one hand, our simulations already told us that yes, the retroreflector characteristics is exactly what we wanted it to be. And in particular, at 50 microns, the structured area appears homogeneously to the naked eye. But it also ensures that you have the full voltage functionality, so it more or less looks, from the naked eye, looks like a smooth surface, but it has a retroreflecting characteristic. Yeah, and if you want to further enhance the reflectivity, you can also tailor this design. For example, if you want to have specific angles to reflect more, with aluminum, if you also change a bit to the design, and you end up, for example, with these structures that you can see from a preliminary work on the bottom right side. And the newest parts can be then seen at our desk. I just received them yesterday. Yeah, that being said, let me just briefly conclude on the key benefits that we see, or in particular what we took out of the results. So basically what we can see is that freeform micro-optics are able to provide new solutions, in particular for tailored light distributions. They enable a compact, multifunctional optical system where various applications are possible, and in particular, for example, with the value chain that we've set up in-house, we are able to provide a cost-effective replication that is enabled by roll-to-roll nano-imprint lithography and step-and-repeat techniques. What is the potential and future perspective that we see, in particular also as RTO? So integration of emerging technologies like an AI-driven or an AI-assisted optical design could definitely streamline the overall design process. I told you before about these feedback loops, so these could be minimized if the AI, for example, can already tell you, okay, you need to consider this rounding or this change in the slope angle of different structures. It is definitely worth thinking about an expansion into green technologies like solar energy and energy efficient lighting, which already is happening. And in general, I think freeform micro-optics offer a transformative solution for new technology innovations. And what is necessary in order to achieve that is basically we need continued research and collaboration in order to unlock the full potential of freeform micro-optics or micro-optics in general for industrial applications. Yeah, that being said, of course that also means that we want to further collaborate, and we would be happy to have you as a partner, as a customer, to address one of these topics like design, origination, also prototyping, power production. We are also producing or are able to develop our own resins, and they can be tailored to meet the stringent requirements, in particular for automotive industry. And for those things we're not able to do in-house, we're really happy to rely on the fabless pilot line, where we have an extended expertise. So with the pilot line, we have access to advanced capabilities and scalable manufacturing. And all in all, that gives really comprehensive solutions. So we're following a collaborative approach to deliver tailored end-to-end solutions for the evolving market needs. Yeah, with that, I'm done with my talk. I'm open for any question, and if you want to discuss anything in more detail, please just stop by at our desk. Thank you.